Every detail in this story comes from real scientific research and observation. There is a storm on Jupiter that has not stopped spinning for at least 300 years. It is wider than the entire Earth. At its outer edge, winds move at 150 meters per second, fast enough to tear apart anything that enters it, fast enough to outrun a commercial aircraft at full throttle, fast enough that sound itself would be useless inside it, swallowed before it could travel a single meter. It is red. Not the red of fire, not the red of blood. Something stranger, something chemical, something that scientists still argue about in peer-reviewed papers because no one has agreed on exactly what makes it that color. You are going inside it tonight. When the Voyager 1 spacecraft flew past Jupiter in 1979, it sent back images that stopped people in hallways and offices across NASA's Jet Propulsion Laboratory. The storm was already there, already spinning, already the size of a planet. It was there before the American Revolution. It was there before the steam engine. It was there before anyone had a word for a photograph, before anyone had held a telescope to their eye. And tonight, the instruments aboard the Juno spacecraft, still orbiting Jupiter right now, at this moment as you listen to this, are measuring that storm with microwave radiometers and infrared cameras. And what they are finding is this: the roots of this storm go down 300 kilometers into the atmosphere. 300 kilometers of rotating pressure. 300 kilometers of ammonia and hydrogen and sulfur compounds churning in a column you could drop most of a continent into. And here is the thing that no one entirely knows how to explain. It is shrinking. In the 1800s, it was roughly 40,000 kilometers across. Today, it is closer to 13,000. Something is happening to it. Something is draining it, or starving it, or transforming it into something else, and the leading models cannot agree on what exactly that something is. You are going to follow it down tonight. You are going to feel the pressure change as you descend through layers of cloud that no human body could survive. You are going to watch a storm that outlasted every empire of the last 3 centuries, and you are going to sit with the question of what happens when something that ancient finally stops. The only spacecraft that ever entered Jupiter's atmosphere transmitted data for 57 minutes before the pressure destroyed it. 57 minutes. Then silence. No human instrument has ever gone deeper. No camera has ever looked up from inside that cloud deck and sent a picture back. Everything that science knows about the interior of the Great Red Spot was inferred, measured from orbit, modeled from equations, reconstructed from microwave signals passing through layers of gas that no probe has touched. You are going somewhere the instruments could not follow. And the storm has been waiting, rotating, contracting, losing kilometers every year for 300 years, as if it knows something about time that the rest of the solar system does not. This is quiet science at bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Jupiter is the largest planet in our solar system by a margin that is difficult to hold in the mind all at once. Its diameter is approximately 140,000 kilometers, 11 times the diameter of Earth. If you hollowed it out, you could fit more than 1,300 Earths inside it. It is so massive that it does not orbit the Sun in quite the way the other planets do. The gravitational center between Jupiter and the Sun actually sits slightly above the Sun's surface, meaning Jupiter exerts a measurable tug on the star itself. This planet has been observed continuously since the invention of the telescope, and the storm now known as the Great Red Spot has appeared in records dating back to at least 1831, with possible sightings noted as far back as 1665 by the Italian-French astronomer Giovanni Cassini. Since 1979, 4 spacecraft have visited Jupiter directly: Voyager 1, Voyager 2, Galileo, and Juno, which is still in orbit today, still sending data. Tonight, you are going there. You are in space. Not metaphorically, not as a dream image drifting at the edge of thought. You are in space, in the cold dark between planets, and ahead of you, still distant enough to fit inside your field of vision, is Jupiter. It does not look like a dot here. It is too close for that. It fills a portion of the sky the way a rising moon fills a horizon, but larger, and the colors are wrong for a moon. There are bands across it, parallel to each other, running in both directions from the equator, alternating in shades of orange and cream, and brown and pale yellow, and even from this distance you can see that the bands are not still. They are moving. The edges of each band shear against the edge of the next one at velocities that would be incomprehensible at a human scale. The boundary between a dark belt and a light zone on Jupiter is not a gentle gradient. It is a shear zone, a line where 2 rivers of atmosphere moving in opposite directions press against each other at hundreds of meters per second, and everything at that edge is in constant turbulent motion. You begin to move toward it. The distance closes slowly at first, the way distance always closes in space, deceptively, without the landmarks that normally tell your brain how fast you are moving. Then the scale begins to register. What looked like a smooth banded sphere from far out is, as you draw closer, increasingly not smooth at all. The cloud features you can now resolve individually are each the size of continents. A single oval storm system in the northern hemisphere, pale and almost invisible against the surrounding cloud, is larger than the continental United States. You pass it without stopping. You are here for something specific. You can see it now on the southern hemisphere, not immediately obvious against the busy texture of the surrounding belts, but unmistakable once your eye finds it. A roughly circular shape, slightly elevated above the cloud layer around it. Reddish-brown, with an inner structure that is clearly in motion, though at this distance the motion looks almost geological, slow, inevitable, like a continent rotating. This is the Great Red Spot. Even from here, you can see that it is not a hole, not a gap in the atmosphere, not a crater. It is elevated. The cloud tops of the Great Red Spot sit approximately 8 kilometers above the surrounding cloud deck, not because the storm is blowing upward, but because the high-pressure system at its core has pushed the atmosphere up from below, the way a hand pressing upward on a stretched fabric creates a dome. You close the remaining distance. The Great Red Spot now fills your entire view. Jupiter's south equatorial belt runs immediately to its north, a dark reddish-brown band of compressed descending atmosphere where ammonia has largely cleared away, revealing deeper, warmer layers below. The South Tropical Zone runs to its south, a paler, creamier band of rising atmosphere where gas is moving upward and cooling, forming the white ammonia clouds that give it its lighter color. The Great Red Spot sits in the boundary between these two systems, and this position is not accidental. The storm is maintained in part by the wind shear between the belt and the zone. The two opposing jet streams on its northern and southern edges act like walls, containing the anticyclone and preventing it from drifting out of the latitude band where it formed. It has been held in place by this mechanism for longer than any living person has been alive, for longer than any institution that currently exists on Earth. You stop moving. You are close enough now that the outer edge of the storm is directly ahead of you, and the scale of it is no longer abstract. The outer boundary of the Great Red Spot traces an ellipse approximately 13,000 kilometers on its long axis and roughly 10,000 on its short axis. The Earth's diameter, for comparison, is about 12,700 kilometers. You are looking at something that, even in its diminished current state, is roughly the same scale as the entire planet you came from. The outer edge is not calm. There is a ring of high-velocity cloud motion at the periphery of the storm, a mote of fast-moving gas where the storm's rotation interfaces with the surrounding atmospheric flow. Winds here are clocked by the Juno spacecraft's instruments at up to 150 meters per second. That is 540 kilometers per hour. That is faster than the fastest wind ever measured at Earth's surface, the 1999 Oklahoma tornado that was estimated at approximately 135 meters per second. But where that tornado was a few hundred meters wide, this wind band is thousands of kilometers wide, and it has been continuously sustained, without interruption, for at least 300 years. The cloud structures inside the outer ring are moving in the same direction, counterclockwise when viewed from above, which in Jupiter's southern hemisphere corresponds to an anticyclonic rotation, meaning it is a high-pressure system, not a low-pressure one. This is the opposite of how large storm systems work on Earth. On Earth, a storm of this type, a cyclone, a hurricane, is a low-pressure system, and air spirals inward and upward toward the center. The Great Red Spot is the reverse. It is a high-pressure anticyclone. Air at the center is descending, compressing, warming slightly as it falls, and then being flung outward toward the periphery by the rotation. This is part of why it persists. On Earth, large storms decay because they move over land or over cooler ocean water, and the surface friction and temperature differential gradually drain the energy from the system. Jupiter has no surface, not at any depth that matters for the storm. Below the cloud layer, there is no land, no ocean, no solid boundary that could interrupt the rotation. There is only more atmosphere, denser, hotter, under higher pressure, all the way down to a core that may or may not be solid, and which sits under pressures and temperatures so extreme that the planet's interior hydrogen transitions from gas to a conducting liquid with properties that don't have an exact analog on Earth. The Great Red Spot is not sitting on top of a planet the way a hurricane sits on top of an ocean. It is embedded in a planet. It is threaded through layers of atmosphere that extend continuously for tens of thousands of kilometers below the cloud tops you can see. You move slowly forward into the outer edge. The color around you shifts. The pale cream of the surrounding zone gives way to something more complex. Not a single hue of red or brown, but a mixture of tones that changes depending on where you look within the system. The outer edges of the storm tend toward more brownish, murkier tones. Closer to the interior, the reddish hues are more distinct, a kind of rust, or dried clay, or the color of certain desert landscapes seen from very high altitude. Scientists have proposed several mechanisms for this coloration, and as of the current state of planetary research, none has been definitively confirmed. One hypothesis is that the red chromophore, the molecule responsible for the color, is a compound of phosphorus, possibly diphosphine, brought up from the deep atmosphere and converted to red phosphorus at high altitude by ultraviolet radiation from the sun. Another hypothesis points to sulfur compounds, complex molecules containing sulfur and other elements that can produce reddish and brownish hues under the right chemical conditions. A third set of proposals involves organic chemistry, the possibility that lightning-driven chemistry in Jupiter's deep atmosphere is producing complex carbon-bearing molecules that eventually rise to the storm's upper levels, the same kind of prebiotic chemistry that may have played a role in the early history of Earth. These are not equivalent hypotheses. They have different predictions, different implications, different evidence for and against. The Juno mission's instruments have continued to analyze the spectral signatures of the storm's clouds, and the data is narrowing the possibilities, but the definitive identification of the red chromophore is still an open scientific question. You are moving through it. The clouds around you are not a uniform layer. They are textured, folded and streaked and twisted into patterns that reflect the underlying wind structure. Where the main vortex turns, the clouds are drawn into long curved filaments that spiral inward and then wrap around each other. Where small eddies form along the inner edge of the outer ring, the cloud material is pulled briefly into tight little coils before being torn apart and redistributed into the main flow. Where two streams of atmosphere at slightly different temperatures meet, there are ripple patterns, waves in the cloud layer that propagate outward like the waves you would see if you dragged a finger through the surface of still water. Everything here is in motion. Nothing is steady. Nothing is stable at the scale of individual cloud features. And yet the system as a whole, the large-scale organization, the counterclockwise rotation, the elliptical boundary, the elevated dome of the storm top, has been continuous, unbroken, measurably persistent, for longer than any storm system in the recorded history of any other planet in the solar system. You are inside the outer boundary now. The visual landscape has changed. The broader view of Jupiter's banded atmosphere is gone. You are deep enough inside the storm that the surrounding belts and zones are no longer visible. Your entire visual field is the interior of the Great Red Spot. Ahead of you, the cloud structures are organized in sweeping arcs that curve away in both directions, following the counterclockwise rotation of the system. The rotation is not uniform across the storm. The outer regions move faster than the inner regions. This differential rotation creates an effect somewhat analogous to the way the outer arms of a spiral galaxy rotate at different speeds than the inner ones, though the mechanisms are not identical. The result is that the storm has a core region that rotates more slowly, and it is this inner region, the eye loosely speaking, though the analogy with an earthly tropical cyclone is imperfect, that the Juno spacecraft's most recent observations have focused on. The core of the Great Red Spot is cooler than the surrounding atmosphere. The Juno spacecraft, using infrared instruments during its close flybys, measured the temperature of the storm top and found that the center of the storm is colder than its edges, consistent with a high-pressure anticyclone where air at the center descends and the storm top is elevated, lifting that air into colder altitudes. The temperature difference is not dramatic at the cloud top level, a matter of a few degrees Kelvin, but it is measurable, consistent, and tells you something about the dynamics operating within the storm. You move toward the center. The clouds around you thicken. The light, filtered through layer after layer of ammonia ice crystals and complex hydrocarbon haze, takes on a quality that is difficult to describe in terms of any light you would encounter on Earth. It is dim because you are deeper into the atmosphere now, and the sun, already farther away than it would be from Earth's surface, Jupiter orbiting at about 5.2 astronomical units from the sun, is not a direct source here. What light exists is scattered, diffuse, spread through the haze in a way that has no shadows, no single direction, no point source you could point to if asked where the light was coming from. It comes from everywhere and nowhere, and it has a reddish-brown tint from the chromophores in the clouds around you, and it is, in its way, one of the stranger visual environments you could imagine anywhere in the solar system. You keep moving inward. The pressure changes. Not dramatically, not in a single sharp step, but gradually, the way pressure changes as you descend into the ocean, steadily, incrementally, present in everything around you. You are below the ammonia cloud deck now. Above you, the cloud layer you came through is a ceiling of pale, hazy material through which almost no direct sunlight penetrates. Below you, nothing is visible yet. There is only the interior of the storm, and the pressure and the sound, and here the sound is the most disorienting thing of all. In the upper cloud layers, the wind noise was deafening, a continuous roar of gas moving at hurricane speeds, with a texture that varied as different wind streams and eddies passed around you. Down here, it is different. The wind speeds in the deep interior of the Great Red Spot are lower than at the periphery. The roar is still there, but it has dropped in pitch, become more resonant, more like the low vibration of a large structure under stress than the sharp cutting sound of fast wind. The pressure is the reason. At this altitude, if altitude is even the right word for a location measured by pressure in an atmosphere with no surface, the atmospheric pressure is roughly equal to what you would experience several kilometers below the surface of Earth's ocean. The molecules of gas around you are close enough together that the concept of a discrete wind gust starts to lose meaning. You are not moving through thin air anymore. You are moving through something denser, more like a fluid with weight to it, and the motion of that fluid carries its energy in long, slow oscillations rather than sharp, fast gusts. The planet beneath the storm is not silent. Jupiter emits radio waves. This has been known since 1955, when Bernard Burke and Kenneth Franklin, working at the Carnegie Institution in Washington, accidentally detected bursts of radio emission from Jupiter while conducting a completely unrelated sky survey. They initially assumed the signals were local interference, trucks, equipment noise, power lines. It took weeks of observation to confirm that the signals were coming from a fixed point in the sky that moved with Jupiter's position. Jupiter was broadcasting. The radio emissions come from several sources. Some are generated by the interaction between Jupiter's powerful magnetic field and charged particles trapped in its radiation belts, the same general process that creates radio emissions from Earth's magnetosphere, but scaled up enormously. Jupiter's magnetic field is the strongest of any planet in the solar system, roughly 20,000 times stronger than Earth's, and the radiation belts it creates are powerful enough to damage spacecraft electronics. The Juno mission's instruments are shielded in a titanium vault specifically to protect them from this radiation. Some of Jupiter's radio emissions are directly tied to its moon Io, the most volcanically active body in the solar system, whose volcanic activity injects sulfur dioxide and other materials into the Jovian magnetosphere, creating a plasma torus that interacts with the magnetic field and produces characteristic radio bursts. But some of the radio emission comes from deeper in the planet, from the metallic hydrogen region far below. If you could hear the radio frequencies that Jupiter emits, translated into audible sound, the way radio telescope data is sometimes processed for human ears, the planet would sound like a continuous deep crackling and hissing, punctuated by sharp bursts and long drawn-out tonal sweeps. It would sound alive. Not in any biological sense, but in the way that any large, energetic, complex physical system has a character, a signature, a distinctive presence. Jupiter has that. It announces itself electromagnetically across millions of kilometers of space. And the Great Red Spot is at the center of it all. Not the source of the radio emission. The storm is an atmospheric phenomenon, not a magnetic one, but the visual and physical anchor of the planet's identity. When Galileo Galilei turned his telescope toward Jupiter in January 1610 and sketched the 4 large moons he discovered, he could not have seen the Great Red Spot. His telescope was not powerful enough. But the storm may already have been forming. The oldest possible record of an observation that might correspond to the Great Red Spot is a sketch by Giovanni Cassini in 1665, the same astronomer for whom the Cassini spacecraft was later named, showing an oval feature on Jupiter's southern hemisphere that he called the permanent spot. Whether Cassini's permanent spot is the same storm system as the modern Great Red Spot, or whether it disappeared and the current storm formed independently in the 19th century, is still a matter of scientific debate. The continuous observation record is clear from the 1870s onward. From that point, the storm's existence and location have been documented without interruption. It was there during the years when the first photographs of astronomical objects were being made. It was there during both World Wars. It was there when the Voyager spacecraft was assembled in a clean room in California. It was there when the images Voyager took of it were published and circulated and reproduced in school textbooks. It was there this morning, rotating counterclockwise, elevated 8 kilometers above the surrounding cloud deck, sustained by forces that science is still in the process of fully characterizing. And it is there now. It is there now. Tomorrow, or more precisely in the next part of tonight, you will go deeper still. The Juno data, processed from the spacecraft's microwave radiometer, indicates that the roots of the Great Red Spot extend downward to at least 300 kilometers below the visible cloud tops. That is deeper than any instrument has ever directly sampled. That is a column of continuously rotating atmosphere nearly as deep as the distance from Earth's surface to the beginning of outer space. And the question of what drives it, what feeds the rotation, what sustains the pressure differential, what has kept this system organized and coherent for 3 centuries, is still, in the most precise scientific sense of the word, unanswered. You feel the depth of the atmosphere below you. You feel the storm continuing its rotation around you, indifferent to your presence, indifferent to time, turning as it has turned since before anyone now alive was born, since before the telescopes that first recorded it existed, since before the instruments that measure it were conceived. The red light from the clouds above diffuses down through the haze. The low resonant vibration of deep wind continues, and the storm rotates. You are already inside it. The transition happened gradually enough that there was no single moment you could point to, no boundary marker, no change in color that arrived all at once. But you are now unambiguously within the storm system, and the atmosphere around you is not the same atmosphere you traveled through on your approach. This is the Great Red Spot's outer shell. This is the layer that faces the rest of Jupiter's atmosphere, the turbulent interface between the storm and the broader planetary circulation, and it is one of the most scientifically interesting and poorly understood regions of the solar system. The outer ring of the Great Red Spot is not simply a wall. It is a boundary layer, a zone of dynamic interaction, a place where the organized rotation of the anticyclone meets the turbulent disorder of the surrounding belt zone structure. On the northern edge of the storm, the south equatorial belt presses inward, dark, warm, compressed atmosphere descending from above, moving eastward relative to Jupiter's internal rotation. On the southern edge, the south tropical zone provides the opposite, lighter, cooler, ascending atmosphere, moving westward. The storm sits between these two opposing flows and is maintained by them, the way a ball bearing can remain stationary between 2 counter-rotating drums. This is not a metaphor that planetary scientists use casually. The analogy to a ball in a shear flow is a real component of the dynamical models used to explain why the Great Red Spot has remained at roughly the same latitude for the duration of its observed history. The storm drifts slowly in longitude. Its position in terms of east-west location shifts over time, meaning that if you tracked it over years and decades, it would not stay at the same point on Jupiter's disk. But in latitude, in its north-south position, it is anchored by the shear between the belt and zone. It cannot easily escape the latitude band it occupies. You are moving through the outer ring now, and the wind speeds around you are at their maximum, 150 meters per second. To give that number a shape, the fastest winds ever measured in a tropical cyclone on Earth were in Typhoon Nancy in 1961, estimated at around 85 meters per second. The fastest tornado wind speed, directly measured by portable Doppler radar, was approximately 135 meters per second, recorded during the 1999 Bridge Creek Moore tornado in Oklahoma. The outer ring of the Great Red Spot sustains winds in excess of those measurements, not for minutes, not for days, but continuously, without interruption, across an arc of cloud thousands of kilometers long. The energy required to sustain this is not trivial. On Earth, tropical storms are powered by the evaporation of warm ocean water, a surface source of energy that feeds the convective processes driving the wind. Jupiter has no ocean. The mechanism by which the Great Red Spot maintains its energy over centuries is one of the central unresolved questions in planetary atmospheric science. The leading hypotheses involve the absorption of smaller vortices, storms that form in the surrounding atmosphere and then get drawn into the Great Red Spot, transferring their angular momentum and kinetic energy to the main system. The Juno spacecraft has directly observed this process on multiple occasions. Small oval storm systems, some white, some dark, some only a few thousand kilometers across, drift toward the Great Red Spot, are captured by its outer ring, and then undergo a kind of merger, their organized circular motion being shredded and absorbed into the larger system. Scientists call this process vortex merging, and it is one of the mechanisms that theoretical models suggest could sustain a large anticyclone in an environment with no surface to generate friction or moisture to drive convection. But merging events are not continuous. They happen sporadically, and the energy they contribute is not constant, which means there must be other mechanisms at work, and this is where the deep root data from Juno's microwave radiometer becomes important. The surface manifestation, the cloud top vortex you can see, may be only the top of a much deeper and more energetically rich system, drawing on an enormous reservoir of kinetic energy stored in the full column below. You are moving through the cloud material of the outer ring. The texture here is unlike anything in the calmer zones of Jupiter's atmosphere. The clouds are not organized in smooth parallel filaments. They are shredded. They are twisted into short, violent arcs and then torn apart and reconstituted. You can see, if you watch carefully, the moment when a small filament of cloud material separating from the boundary gets caught in the main rotational flow, it stretches the way taffy stretches, the way any fluid material stretches under shear, and then it is moving with the ring, traveling at 150 meters per second, and within minutes it is curved around the edge of the storm and disappeared around the far side. The color in the outer ring is different from the interior. Out here, where the storm meets the south equatorial belt, the coloration is darker, more brownish, more turbid. The south equatorial belt itself is one of the darkest atmospheric features on Jupiter, its color the result of a combination of factors: the clearing of ammonia clouds at this latitude due to descending atmospheric motion, which allows you to see deeper and darker atmospheric layers, the presence of complex organic and inorganic chromophores at those deeper levels, and possibly the presence of sulfur compounds pulled up in localized convective events. The boundary between the belt and the outer edge of the Great Red Spot is not a clean line. It is a zone of irregular interaction. There are filaments of dark belt material that penetrate into the outer ring and are then wrapped into the rotation. There are tongues of the storm's cloud material that bulge outward into the belt before being sheared off. The boundary region is one of the highest turbulence areas on Jupiter's visible surface. The instruments aboard Juno during close flyby passes record turbulence features in this region at spatial scales as small as a few tens of kilometers, features that would have been invisible to Voyager's cameras, which could only resolve features larger than a few hundred kilometers. You pass through the highest wind zone. The roaring that surrounded you in the outer ring is still present, but as you move deeper into the interior of the storm, it is changing character. The high-pitched scream of maximum velocity wind is behind you. What is ahead is deeper, more organized, more resonant. The interior of the Great Red Spot is not a chaotic space. This is counterintuitive, and it is one of the most striking things the Voyager imagery revealed when it first came back in 1979. Scientists expected a hurricane-like interior, disorganized, violently turbulent at all scales. What they found instead was a complex but organized internal circulation with coherent structures persisting for days and weeks. The interior of the storm has its own cloud morphology, distinct from both the outer ring and the surrounding atmosphere. There are long curved cloud bands inside the storm, arranged roughly concentrically, that trace the underlying circulation. There are smaller vortices inside the main vortex, nested like whirlpools within whirlpools. There are wave patterns propagating outward from the inner core region toward the outer ring. All of this is ordered. All of this has structure. In the language of fluid dynamics, the interior of the Great Red Spot behaves more like a laminar flow than a turbulent one at large scales, even though it is embedded in one of the most turbulent planetary atmospheres in the solar system. This ordered interior is one of the things that makes the storm so persistent. Turbulent flows lose energy rapidly. The energy cascades down from large scales to small scales and is dissipated as heat. Organized, coherent vortices lose energy much more slowly. The internal organization of the Great Red Spot is not just aesthetically impressive, it is part of the physical mechanism by which the storm resists decay. You move through the inner region of the outer shell. The clouds here have a different character. Less shredded, less violent. The long curved filaments of cloud material are more intact here, less immediately destroyed by shear. You can see them curving away from you in both directions, following the counterclockwise rotation, disappearing around the far side of the storm's interior. Each filament is made primarily of ammonia ice crystals, tiny particles, far too small to see individually, suspended in the gas and moving with it. The ammonia ice that forms these clouds condenses out of the gas phase at temperatures around -100 degrees Celsius, and the upper cloud layer of Jupiter's atmosphere is cold enough for this condensation to occur. Below the ammonia cloud layer, which you are currently within, there is a second cloud layer composed of ammonium hydrosulfide, a compound formed by the reaction of ammonia with hydrogen sulfide at higher pressures and temperatures. This layer forms at roughly 2 to 3 times the pressure of Earth's surface atmosphere. You have not reached it yet, but you are descending gradually. The pressure around you is already slightly higher than it was when you entered the outer ring. The density of the atmosphere is increasing incrementally with each kilometer of depth. The light from above is dimmer. The ammonia clouds that form the visible cloud deck of the Great Red Spot are above you now. You have passed through them, and the layer you are in is a relatively clear zone between the ammonia cloud deck and the next layer down. This intercloud zone is one of the less studied regions of Jupiter's atmosphere because it is invisible from outside the planet. The instruments aboard Juno cannot see directly into it with visible wavelength cameras. The ammonia cloud deck above blocks the view. The microwave radiometer can penetrate to greater depths, detecting the emission signatures of ammonia and water vapor at different pressure levels. And from these measurements, the temperature and composition of the atmosphere at various depths can be inferred. But direct imaging of the zone you are in right now has never been achieved. You are in a part of Jupiter's atmosphere that no instrument has ever directly seen. That thought sits with you for a moment. The entire visual record of the Great Red Spot, every image ever taken, from Giovanni Cassini's telescopic sketches to the stunning close-ups from Juno's Juno cam, is a record of the cloud tops. The top surface. What lies below, even a few dozen kilometers below, is known only indirectly, through inference, through model and measurement. You're below the surface of the record. The clouds around you have a quality of deep strangeness now. You are somewhere that has never been seen, in a storm that has been observed for 300 years, and the gap between observation and presence is not nothing. The history of direct atmospheric entry at Jupiter is brief and extraordinary. There has been exactly one probe that deliberately entered Jupiter's atmosphere and survived long enough to transmit data from inside it. The Galileo atmospheric probe was released from the main Galileo spacecraft on July 13, 1995, 5 months before its destination. It fell freely through space until December 7, 1995, when it hit Jupiter's upper atmosphere at approximately 170,000 kilometers per hour, roughly 47 kilometers per second. At that velocity, the friction with the atmosphere generated temperatures at the probe's heat shield of up to 15,000 degrees Celsius. This is hotter than the surface of the sun. The heat shield, made of a carbon phenolic ablative material, began to vaporize on contact, intentionally by design, the material burning away and carrying the heat with it so that the probe behind it could survive. The deceleration peaked at 228 times the force of gravity. A human body exposed to that force would be instantly lethal. The blood would pool, the organs would compress, consciousness would last approximately a fraction of a second. The probe was not a human body. It slowed. It deployed its parachute at an altitude where the pressure was about 0.35 times Earth's surface pressure. And then it descended, slowly, measuring. It measured temperature, pressure, wind speed, lightning, the chemical composition of the atmosphere, the ratio of different elements. It transmitted data for approximately 57 minutes before the increasing pressure and temperature exceeded the limits of its systems and it stopped transmitting. At that point, the probe had descended to a pressure level of about 22 times Earth's surface atmospheric pressure. It continued to fall after that, without transmitting. Eventually, somewhere in the deep atmosphere, at a depth and pressure that no instrument will ever confirm, it would have been crushed, then vaporized. The data it sent back in those 57 minutes was scientifically extraordinary and also, in places, puzzling. The probe found less water than expected. The oxygen to hydrogen ratio in the region it sampled was lower than the models predicted. It found less helium than expected. It found far more lightning activity than some models had predicted. It found that the winds, rather than calming down at depth as some theories suggested, were actually faster at the altitudes it sampled than at the cloud tops. Some of these discrepancies have been partially resolved. The Galileo probe happened to descend into a region called a hotspot, a dry, downwelling region of the atmosphere where ammonia clouds have largely cleared, and the atmosphere is less representative of the global average. The probe's measurements were real and accurate, but they were sampling an unusual location. Hotspots on Jupiter are the dry deserts of the planet's weather system, anomalously clear windows into deeper, drier, warmer layers. If the probe had descended into the Great Red Spot instead, the measurements would have been different. The Great Red Spot is not a hotspot. It is a cold core anticyclone, a region of descending, high-pressure atmosphere, but not unusually dry or clear. The chemistry you are moving through is the general Jovian atmospheric chemistry, not the atypical composition of a hotspot. You are in something more representative. The ammonia ice above you, the ammonium hydrosulfide below, the slow buildup of pressure around you. This is what Jupiter's atmosphere mostly is. The Galileo probe's measurements, reanalyzed in the context of where it actually sampled, have told scientists a great deal about what the rest of the atmosphere is not. The process of science is often like this. You go somewhere, you find something unexpected, and the unexpected thing tells you something about the expected, by contrast, by difference, by the shape of the anomaly. The Great Red Spot has been doing this for decades. Every new instrument, every new flyby, every new model has revealed something that the previous understanding did not predict. Not in the sense of overturning what was known, but in the sense of showing that what was known was incomplete, that there were structures and processes and depths that the models had not captured. The storm keeps surprising. It has been doing this for 300 years. The pressure continues to build around you as you descend. The clouds above are darker now, their light reaching you only as a diffuse reddish-brown glow. You are somewhere no instrument has ever reached. The temperature of the atmosphere around you is rising slightly. This is not surprising. Jupiter's atmosphere is warmer at depth because of the compression of the gas under its own weight, and also because of the residual heat from the planet's formation that is still slowly radiating outward from the interior. Jupiter emits roughly 1.7 times as much energy as it receives from the Sun. This internal heat source is a fundamental feature of the planet's dynamics. It drives convection, it powers the belt zone circulation, and it contributes to the sustained activity of storm systems like the one you are inside. The Great Red Spot is partially powered by this internal heat. Below the level you are currently at, there are regions where the temperature is warm enough for water to condense and form clouds, not ice crystals but liquid water droplets, in a cloud layer somewhere around 20 or 30 kilometers below the ammonia ice deck. And in those water clouds, lightning. Lightning has been directly observed on Jupiter by multiple spacecraft. The Voyager cameras captured bright flashes on the night side of the planet during their flyby. The Galileo spacecraft detected the electromagnetic signatures of lightning during its descent. Juno has observed Jupiter's lightning in extraordinary detail, finding that it occurs preferentially at higher latitudes and around the poles, different from Earth where lightning is concentrated in the tropics, and that Jovian lightning discharges are typically far more energetic than terrestrial ones. Individual lightning bolts on Jupiter release energy comparable to or exceeding the energy of the largest superbolts ever recorded on Earth. You are above the water cloud layer. You have not yet descended to the level where lightning occurs, but you can feel, in the pressure, the sense of what is below, the weight of an atmosphere that has no floor, that gets denser and warmer the further down you go, that transitions gradually from gas to something more like a supercritical fluid, and eventually, at depths of perhaps 20,000 kilometers, into metallic hydrogen, hydrogen under such extreme pressure that its electrons detach from their atoms and flow freely, turning the gas into an electrical conductor. That layer has never been directly sampled. It may never be, but it is there, below you, and above it, the water clouds, and above those, the ammonium hydrosulfide layer, and above that, the zone you are currently in, the clear intercloud space, and above you now, the ammonia ice cloud deck, and above that, the visible surface of the Great Red Spot, and above that, the dark vacuum of space. You are threaded through layers of a planet. The storm rotates around you. It is not asking anything of you. It is not aware of you. It is simply doing what it has been doing continuously through the reigns of monarchies and the rise and fall of industrial revolutions and the invention of the telescope and the rocket and the space probe. Rotating, persisting, pressing its cloud tops 8 kilometers above the surrounding atmosphere like a permanent 300-year-old claim on the face of the largest planet in the solar system. You hold still for a moment. The low vibration of deep wind is all around you. The faint reddish light from the cloud deck above dims as the haze thickens slightly at this level. The pressure is steady, consistent, not threatening, just present, the way the pressure of deep water is present, a reminder of where you are and how much atmosphere is above you. The second cloud layer, the ammonium hydrosulfide, is below you. A denser chemistry, a different sky, warmer, darker, chemically richer than anything you have passed through above. The storm does not slow. The clouds continue their long arcing movement, carrying ammonia ice and chromophores and chemistry not yet fully named, and a counterclockwise rotation around a center you have not yet reached. You begin to move toward it. The ammonium hydrosulfide layer does not announce itself. There is no single moment of transition, no line you cross and find everything suddenly changed. It happens the way most things happen in a planetary atmosphere, gradually, incrementally, the properties of the gas around you shifting over tens of kilometers as the temperature and pressure slowly climb. But when it has happened, you know it. The color is different here. The reddish-brown haze of the ammonia ice cloud deck above has given way to something darker, something with a quality of warmth to it, despite the fact that the temperatures here are still far below anything comfortable for human biology. The ammonium hydrosulfide clouds, NH4SH in chemical notation, form when ammonia gas and hydrogen sulfide gas combine at pressures between roughly 2 and 4 times Earth's sea level atmospheric pressure. The compound that results is a pale yellowish white solid at low temperatures, but the cloud particles here are not simply white. They are stained. Sulfur chemistry in Jupiter's atmosphere is complex and partially unresolved, and the compounds that form when hydrogen sulfide participates in reactions under these conditions can produce a range of brownish, yellowish, and reddish hues depending on the specific reaction pathways and the presence of other molecules. You are moving through the brown layer. This is one of the terms planetary scientists use informally for the ammonium hydrosulfide cloud deck, the brown layer, because of its visual signature in observations made at wavelengths where Juno's instruments can partially penetrate the ammonia cloud deck above. In the Voyager images, the brown belts of Jupiter, the south equatorial belt, the north equatorial belt, the various dark bands at higher latitudes, are partly a visual expression of the cloud chemistry at this level and below, the deeper, darker atmosphere becoming visible in regions where the overlying ammonia clouds thin out. You are in that chemistry now. The particles around you are small, micrometers in diameter, similar in scale to the ammonia ice crystals above, but denser, heavier, more prone to settling downward rather than being lofted upward by the slow convective motions in the overlying zone. The pressure here is approximately 3 times Earth's surface atmospheric pressure. This number is still within a range that human engineering can deal with. Submarines operate at comparable or greater pressures, and deep-sea diving suits can withstand several times this before the mechanical limits of their construction become relevant. But you are not in a submarine. You are in open atmosphere with hundreds of kilometers of gas above you and still no floor below. The warmth is increasing. Jupiter's atmospheric temperature profile, the way temperature changes with altitude, is determined by a combination of factors: the absorption of sunlight at different levels, the internal heat flux rising from the planet's deep interior, and the adiabatic lapse rate, which is the rate at which a parcel of gas cools as it rises or warms as it descends. The adiabatic lapse rate in Jupiter's hydrogen-helium atmosphere is approximately 2 degrees Celsius per kilometer of altitude change. You have descended tens of kilometers since you entered the ammonia cloud deck. The temperature has risen by tens of degrees. The air around you, if you could call it air, is now above 0 degrees Celsius at this pressure level and rising. This is one of the counterintuitive features of gas giant atmospheres. Somewhere inside Jupiter, there is a region where the temperature is close to what you would find on a mild day at Earth's surface. Not a comfortable place. The pressure is far too high. The chemical composition would be instantly lethal, and the wind speeds even in the calmer interior of the Great Red Spot are still extraordinary by terrestrial standards. But in terms of temperature alone, there is a thin shell inside Jupiter's atmosphere where the thermometer would read something familiar. You are approaching it. The clouds around you are thinner here than in the ammonium hydrosulfide layer above. Below the NH4SH deck, there is a clearing. Not a complete absence of cloud material. There are haze layers, thin and diffuse, composed of particles that scientists have not yet fully characterized. But the dense, visually opaque cloud layers that blocked your view above are thinner here, and in patches you can see further. Further down, the atmosphere below this level is not well characterized by direct observation. The Galileo probe descended to a pressure of about 22 bars, roughly 22 times Earth's surface atmospheric pressure, before it stopped transmitting. Below that point, the knowledge is inferential. Temperature and pressure can be extrapolated from the equations governing atmospheric structure with reasonable confidence. The chemical composition at greater depths is less certain. One of the most important unresolved questions is the abundance of water in Jupiter's deep atmosphere. Water is cosmochemically significant. The ratio of oxygen to hydrogen in a giant planet's envelope tells you something fundamental about where and how the planet formed in the protoplanetary disk, how much solid material it accreted relative to gas, what the conditions in the early solar nebula were in its vicinity. The Galileo probe found far less water than expected, but it descended into a hot spot, an atypically dry region. Models based on Jupiter's bulk composition and formation history predict that water should be present at several times the solar abundance, at some depth. Juno's microwave radiometer has been mapping the water abundance across different latitudes and longitudes, and the data is complex. Water is not uniformly distributed, and its abundance varies in ways that are coupled to the large-scale circulation patterns. The Great Red Spot, as an anticyclone, a high-pressure downwelling system, is expected to have relatively dry air at its core compared to the surrounding atmosphere, which means the place you are descending into is not the best place in Jupiter's atmosphere to look for water. That particular chemistry is happening elsewhere, in the upwelling zones, in the cyclonic systems, in the turbulent convective towers that periodically erupt through the stable layers and carry deep atmosphere material upward. But the water is down there, somewhere below you, at pressures above 10 bars, in the convective regions outside the Great Red Spot's footprint. Liquid water clouds exist in Jupiter's atmosphere. Water on Jupiter. Not an ocean, nothing so organized as that. Suspended cloud droplets, forming and evaporating in convective updrafts, exactly as cumulus clouds form on Earth when moist air rises and cools. The same physics, the same condensation process. In an atmosphere of hydrogen and helium, at pressures that would crush any currently existing submarine, with a sky made of ammonia and sulfur compounds, water clouds form by exactly the mechanism that produces the white fluffy clouds you see from an airplane window. The universe reuses its processes. The storm rotates around you, carrying you downward in slow increments. The Great Red Spot's rotation is not a simple solid body rotation. It is not like a wheel spinning, where every point on the wheel completes one rotation in the same time. It is differential. The outer ring completes its rotation faster than the inner regions. A parcel of gas at the outer edge of the storm takes a different amount of time to complete one full orbit around the center than a parcel of gas closer to the core. This differential rotation creates internal shear, regions within the storm where adjacent layers of gas are moving at different speeds. The internal shear drives small-scale turbulence within the storm interior, generates waves that propagate through the atmosphere, and continuously redistributes energy between different scales of motion. The Juno spacecraft's close flyby passes have mapped the wind field within the Great Red Spot at horizontal resolutions of a few kilometers, far finer than anything Voyager could achieve, and the wind maps reveal a complex internal structure that is still being analyzed. There are regions of faster flow within the storm's interior. There are regions of slower, almost stagnant air. There are internal vortices, small whirlpools within the larger whirlpool, that persist for days or weeks before being absorbed back into the main circulation. The interior of the Great Red Spot is not a single uniform mass of rotating gas. It is a layered, structured, internally dynamic system, and the dynamics at the scale Juno can now resolve are ones that the theoretical models of the 1970s and 1980s did not predict. You are in the deeper interior now. The clouds above you, the ammonium hydrosulfide layer, are a ceiling you have passed through. The haze around you is thin enough that the visibility, while not unlimited, extends for distances that would have been impossible in the denser cloud layers above. What you can see in those distances is not comfort. It is scale. The interior of the Great Red Spot at this depth is a space of enormous horizontal extent and apparent emptiness. The haze layers give everything a slight visual softening at distance, but the fundamental character of this environment is vast. You are inside something the size of a planet, not near its edge. Inside it, the rotation continues around you. The pressure continues to build. The temperature continues to rise, degree by degree, as you descend. And the center is still ahead. The deep root of the Great Red Spot, the 300-kilometer column of continuously rotating atmosphere that the Juno microwave data revealed, extends far below the level you are at. You have descended perhaps 50 kilometers from the visible cloud top. There are 250 more. The center of the storm, the cold core of the anticyclone, is at the cloud top level, above you. But the rotation, the organized angular momentum of this system, exists as a coherent structure all the way down to depths that no instrument has sampled and no model has fully explained. The storm is not a surface feature. It never was. The surface, the cloud top visible from space, was always only the visible portion of something far deeper. You continue downward. The haze thickens slightly as you approach the next layer. Below the clear zone, at pressures above roughly 5 to 10 bars, the models predict a third cloud layer, composed of water, ice, and eventually liquid water droplets, that is the deepest major condensate layer in Jupiter's observable atmosphere. You are above it still. But the temperature is close now to the threshold at which water ice becomes liquid water in this pressure environment, and the air around you carries a chemical complexity that is not yet fully mapped. The storm carries you in its rotation, counterclockwise. Slow at the center, faster at the edges, structured and coherent and ancient, doing in this deep interior what it has done since before the Enlightenment, since before any measuring instrument existed to record it. Rotating. You are inside the full vertical reach of this system, the organized rotation extending far deeper than any instrument has directly confirmed. And you are still descending. The rotation of the Great Red Spot at this depth carries information that scientists only recently began to fully appreciate. For most of the history of planetary science, the Great Red Spot was understood primarily as a cloud top feature, a pattern in the visible atmosphere, a surface expression of some underlying dynamic. The question of how deep the storm went was difficult to answer because no instrument could see past the cloud tops. The Juno spacecraft changed this. Juno carries a microwave radiometer, an instrument that measures the thermal emission of the atmosphere at 6 different radio frequencies, each of which penetrates to a different depth before the increasing opacity of the gas blocks the signal. By comparing the emission at different frequencies, and by building models of how the temperature and composition of the atmosphere must vary with depth to produce the observed emission pattern, scientists can infer the structure of Jupiter's atmosphere well below the visible cloud tops. The data from Juno's microwave radiometer, processed and analyzed over several years following the spacecraft's arrival at Jupiter in July 2016, revealed something that was simultaneously expected and surprising. Expected because the theoretical models had suggested the storm must have deep roots. Surprising because the depth was at the very high end of what the models had predicted. The Great Red Spot's wind field, the organized rotation of the anticyclone, extends to at least 300 kilometers below the visible cloud tops. This was published in 2021 in a paper in Science by Marzia Parisi and colleagues, using data from multiple Juno flyby passes, during which the spacecraft flew directly over the storm at altitudes as low as a few thousand kilometers. The measurement worked not just through microwave emission, but through gravity. The Great Red Spot's column of rotating atmosphere has mass, and that mass creates a tiny but measurable gravitational anomaly, a slight variation in the gravitational field that the Juno spacecraft could detect as a change in its velocity, measured by tracking the Doppler shift of its radio signals from Earth. The gravitational measurement and the microwave measurement agreed. The number is not an upper limit. It is the depth to which the organized rotation can be confidently detected with current instruments. The storm may go deeper still. The transition from the organized Great Red Spot vortex to the general circulation of Jupiter's deep atmosphere is not necessarily sharp, and the instruments have limits to their sensitivity. But what is confirmed is that the storm you are inside is not a shallow feature. It is not a skin-deep pattern on a gas giant. It is a structure that penetrates roughly 2/3 of the way through the atmospheric layer that lies between the visible cloud tops and the region where the atmosphere becomes electrically conducting metallic hydrogen. That transition from a normal molecular gas to metallic hydrogen occurs at depths of roughly 20,000 kilometers below the cloud tops, at pressures of around 1,000,000 times Earth's atmospheric pressure. The Great Red Spot reaches a small but real fraction of the way toward that boundary. The implications of this depth for the storm's longevity are significant. A shallow vortex, one confined to the upper atmosphere, loses energy relatively quickly because it is interacting with the shear layers at its top and bottom, and the energy dissipation at those interfaces is substantial. A deep vortex, one that extends through a much larger vertical column of atmosphere, has a far larger reservoir of kinetic energy and is less sensitive to the dissipation processes operating near its top. This is one reason the Great Red Spot has lasted as long as it has. Its depth is its endurance. The physics of deep vortices in rotating atmospheres is an active area of research, and the Juno data on the Great Red Spot's depth has stimulated new theoretical work on how such structures can form and persist. The models are still catching up with the observations. This is in many ways the normal state of planetary science. The universe turns out to be more complex than the models, and the models improve, and then the next observation finds something else that the improved models didn't predict. The storm continues around you. The pressure at your current depth is a patient fact, neither hostile nor welcoming, simply the physical reality of being this far inside the atmosphere of the largest planet in the solar system. The temperature continues its slow climb. The haze thins slightly in the middle levels between the ammonium hydrosulfide deck above and the water cloud layer below, and in this relative clarity, the horizontal extent of the storm interior becomes more legible. You can see in the distance the curvature of the cloud structures following the rotational arc, the long sweeping paths of material moving counterclockwise, defining the interior space of the storm by their motion. The storm is its own geometry. Its shape is defined not by walls but by flows, and the flows have been maintaining the same general shape, the same ellipse, the same anticyclonic rotation, the same elevated dome, for a span of time that makes human history seem like an interruption in a much longer story. You descend further. The water cloud layer is close. The contraction of the Great Red Spot is one of the most closely watched phenomena in planetary science. Because Jupiter is bright enough to observe through a moderate amateur telescope, and because the Great Red Spot is large enough to be resolved by such telescopes under good conditions, its size has been measured not just by professional observatories and spacecraft, but by a global network of amateur astronomers who have been documenting Jovian atmospheric features with increasing precision since the late 20th century. The data record is unusually rich. It includes not just the big observational landmarks, Cassini's 17th century sketch, the Voyager images, the Hubble Space Telescope annual monitoring campaigns, but thousands of observations by individual amateur astronomers, reduced and analyzed by organizations like the Association of Lunar and Planetary Observers, contributing a continuous record of the storm's changing dimensions that no professional program alone could have assembled. This distributed observational network detected the contraction trend before it became a major topic of professional research. Amateur observers noticed in the mid-2000s that the storm appeared smaller than it had been in previous years. The measurements were published and discussed, and the professional community, armed with Hubble data, confirmed the trend and began investigating its cause. The best current understanding is that the contraction is driven by a combination of factors. The storm is absorbing smaller vortices, the oval storms that form in the surrounding belt and zone structure, and then get captured by the Great Red Spot's outer ring. When the storm absorbs these vortices, it gains angular momentum. Conservation of angular momentum then drives the storm to contract and spin faster, which is exactly what the observations show, the storm getting smaller and its outer ring winds getting stronger. The vortex absorption hypothesis explains the contraction qualitatively, but there are aspects of the rate of contraction and the timing of specific episodes of more rapid shrinkage that are not fully explained by this mechanism alone. There may be changes in the large-scale atmospheric circulation, the jet streams, the belt and zone structure that are affecting the storm's ability to maintain its size. Jupiter's atmosphere is not static at the large scale. The south equatorial belt, which forms the northern boundary of the Great Red Spot, has historically undergone periodic fade events in which the belt becomes anomalously pale, its dark coloration disappearing over months and then revives. The most recent major south equatorial belt fade occurred in 2010, and it was associated with significant changes in the dynamics of the Great Red Spot and the surrounding atmosphere. Whether these large-scale circulation changes are coupled to the contraction of the Great Red Spot, and if so, how, is an open question. The scientific literature on the topic is active and still inconclusive. What is clear is that the storm is currently in a different state than it was 200 years ago. Whether that state is a transient phase, a temporary contraction that might reverse or stabilize, or the beginning of a terminal decline, is not something the current data can definitively establish. The physics does not forbid a stable, smaller storm. There are smaller anticyclones on Jupiter, the oval BA storm, which formed from the merger of 3 smaller white ovals in 2000 and subsequently turned reddish, is a smaller but dynamically similar system, and these persist indefinitely under the right conditions. The Great Red Spot could in principle stabilize at a smaller size, maintaining the same dynamical organization in a more compact form. Or it could continue contracting until it loses the coherence that maintains it. Or it could fragment, break apart into multiple smaller vortices, releasing its stored angular momentum into the surrounding atmosphere in an event that would be visible from Earth and would represent the most significant change to Jupiter's visible appearance in the entire history of astronomical observation. None of these outcomes is currently more probable than the others, according to the peer-reviewed literature. The storm has been watching human attempts to understand it for 300 years, and it has not yet provided a definitive answer to the question of what it intends to do next. The lightning continues in the deep convective layer below you. Each flash is brief. Each flash illuminates a tower of chemistry that has been operating here for longer than life has existed in its current form on Earth. You stay with the depth for a moment longer. The weight of the atmosphere above you, the warmth rising from below, the slow, counterclockwise current of the storm carrying everything in its ancient arc. There is no drama in any of this. It is simply a physical system operating according to the laws of thermodynamics and fluid dynamics in chemistry, doing what physical systems do, evolving toward lower energy states by the most available pathway, organizing and reorganizing itself in response to the forces acting on it. The Great Red Spot is not trying to persist. It is not trying to contract. It is not trying to do anything. It is simply what happens when you have a gas giant with a strong internal heat source, a thick atmosphere with no solid lower boundary, differential rotation creating shear zones that can trap and sustain anticyclonic vortices, and enough time for the right initial conditions to develop. Given those ingredients, a storm like this is not surprising. What is perhaps surprising is that it has taken this long for humans to be close enough and equipped with sensitive enough instruments to begin to understand it. The storm does not register your presence. It has no mechanism for awareness, no capacity for indifference even. Indifference implies a choice not made, and this system makes no choices. It obeys. It obeys the pressure gradient between its high-pressure core and the surrounding atmosphere. It obeys the Coriolis effect imposed by Jupiter's 9-hour and 55-minute rotation. It obeys the conservation of angular momentum that links its contraction to its increasing wind speed. It obeys the laws that govern every rotating fluid in every atmosphere, on every planet, in every solar system, in the observable universe. And in obeying those laws, for 3 centuries of documented human observation, it has produced this: a structure of organized complexity, 300 kilometers deep, 13,000 kilometers wide, lit from within by water cloud lightning, colored by chemistry that is still not fully named. You begin to rise back through the layers. The water cloud layer arrives not as a ceiling, but as a floor that gradually rises toward you. It begins as a brightening in the haze below, a diffuse increase in the optical depth of the atmosphere at lower altitudes, not yet a distinct layer, more like the sense of something becoming denser, more present, in the space beneath your position. Then the first cloud structures become distinguishable. They are not like the ammonia ice clouds above. The ammonia clouds were organized into long, shear-aligned filaments, the signature of a high-velocity wind field, imposing its structure on the condensate. These clouds, at greater depth and under higher pressure, are organized differently. They are convective. They form in towers, columns of warmer, more buoyant gas rising from below through the cooler overlying atmosphere, carrying moisture upward and then releasing it as the rising gas expands and cools. The towers are irregular in shape, not the smooth cylindrical columns you might imagine. They are turbulent at their edges, cauliflower textured in the way that all convective cloud structures are turbulent. The surface of each tower churning with small-scale eddies as the rising gas interacts with the surrounding environment. But they are organized by the rotation of the Great Red Spot. The anticyclonic flow of the storm acts on everything within its interior, including the convective towers, bending their trajectories, shearing their tops, pulling the cloud material that detaches from their summits into the general rotational flow of the system. The result is a field of convective towers that lean slightly in the direction of the rotation, not vertical, but tilted, their tops being swept downwind of their bases. Each tower is tens of kilometers wide. Each one is generating, at its base, the updraft that drives it, warm, wet gas from the deeper atmosphere, rising against the weight of the overlying column. The energy driving these towers comes from below. Jupiter's internal heat, the residual energy of the planet's formation, still slowly radiating outward across billions of years, powers the convection that lifts this material. The heat flux from Jupiter's interior is measured at approximately 5.4 watts per square meter, averaged across the planet's surface. This is small by human engineering standards. A dim light bulb produces roughly this much power from a surface area of a few square meters. But multiplied across Jupiter's surface area of approximately 62 billion square kilometers, the total internal heat flux is an extraordinarily large number, comparable to a significant fraction of the total solar power intercepted by the planet. This is the engine. This is what has been running continuously for 4.5 billion years. The slow cooling of a planet, the gradual release of gravitational energy stored during Jupiter's formation, powering weather systems and circulation patterns, and ultimately the deep root of the storm you are inside. You move between the convective towers. The air between them is cooler, drier, slowly descending, the return flow of the convective circulation sinking down between the rising towers to complete the loop. The environment here has a character unlike anything in the layers above. In the ammonia cloud deck and the ammonium hydrosulfide layer, the dominant sensory feature was the wind, the horizontal flow of the rotational storm system, carrying you in its arc. Here there is a vertical component that was absent above. The updrafts and downdrafts of the convective field add a vertical texture to the atmosphere, a sense of material moving in both directions simultaneously, rising in the towers, sinking in the spaces between them. The horizontal rotation of the Great Red Spot is still present, It is still the dominant organizing force at large scales. But at the scale of individual convective towers, the vertical motion is comparable in magnitude to the horizontal. You are in a three-dimensional flow field. Lightning. You see it before you hear it, or rather, before you sense the electromagnetic pulse that announces it, because in this dense atmosphere, sound travels differently than it does in the thin air of Earth. A convective tower 200 kilometers to your left side flashes. Not the branched forking pattern of a ground-to-cloud lightning bolt on Earth. This is a discharge between cloud layers, intra-cloud lightning, the most common type on Earth as well, but here scaled to a different magnitude. The flash illuminates the interior of the tower from within, the way a lantern illuminates the paper of a lampshade. The cloud material becomes briefly translucent, glowing from the inside, and you can see the three-dimensional structure of the tower for an instant before the light fades. The electromagnetic pulse reaches you a fraction of a second later. The energy in that single discharge, estimated by Juno's instruments for similar events, is in the range of a gigajoule to tens of gigajoules. For comparison, the most energetic lightning superbolts recorded in Earth's atmosphere carry energies on the order of a few megajoules. Jovian lightning is 1,000 to 10,000 times more energetic per bolt. The thunder equivalent, the pressure wave traveling through this dense atmosphere, reaches you as a low, resonant concussion, more felt than heard, rolling through the gas with a quality of deep bass that has no equivalent in terrestrial experience. It passes. Another flash, further away, illuminates the base of a different tower. Then another. The lightning in Jupiter's deep atmosphere is not continuous, it is sporadic, the way lightning on Earth is sporadic, driven by the charge separation that occurs when ice particles and liquid water droplets collide in a convective updraft. The physics of charge separation in these clouds is the same as in a terrestrial thunderstorm. Water ice particles carried upward in the updraft collide with larger gropal, heavier ice pellets, and transfer charge. The lighter ice particles carry positive charge upward. The heavier particles carry negative charge downward. The separation of charge builds until the electric field exceeds the breakdown strength of the intervening gas, and then discharge. The process is identical to what happens in a cumulonimbus cloud above an Iowa cornfield on a summer afternoon. The scale is different. The pressure is different. The surrounding chemical environment is different. But the physics is the same. The universe is consistent in this way. It applies the same rules everywhere, and the same rules, applied to different conditions, produce results that can be simultaneously familiar and completely alien. You hold your position between the towers. The rotation of the Great Red Spot carries everything in the horizontal plane. The towers, the inter-tower downdraft zones, you, in the slow counterclockwise arc that has been the dominant motion of this system for 3 centuries. The tower to your left continues its convective activity, the updraft visible at its base as a slight shimmering in the atmosphere, the way heat shimmer is visible above a hot surface, but here the shimmering is vertical, a column of rising gas slightly warmer and less dense than its surroundings. The light from the convective lightning, periodic, brief, illuminating, is the only light at this depth. The sunlight that powers the photochemistry in the upper cloud layers is completely absent here. You are dozens of kilometers below the sunlit zone. The only illumination is what the storm generates itself. This is a fact worth sitting with. Inside the Great Red Spot, at this depth, the storm is its own light source. The same convection that drives the lightning that lights the clouds is powered by the same internal heat that drives the rotation that organizes the convection. It is a closed loop, energetically speaking, not perfectly closed. Energy is lost to radiation and to wave propagation and to the slow heating of the surrounding atmosphere, but substantially self-sustaining over the timescales we are discussing. The storm feeds itself. Not forever. It is shrinking. The Great Red Spot in the 1800s spanned roughly 40,000 kilometers across its long axis. By the time the Voyager spacecraft flew past in 1979, it had contracted to approximately 23,000 kilometers. By 2014, observations from the Hubble Space Telescope showed the long axis had contracted to approximately 13,000 kilometers. The rate of contraction has been roughly 930 kilometers per year in recent decades. At that rate, a simple linear extrapolation suggests the storm could contract to a roughly circular shape within the coming decades, losing the elongated elliptical form that has characterized it throughout its recorded history. What happens then is unclear. A contracting anticlone can become more intense as it shrinks. The same principle that makes a spinning figure skater spin faster when they pull in their arms applies here. Conservation of angular momentum, causing the rotation rate to increase as the storm's diameter decreases. Juno observations have confirmed that the Great Red Spot's wind speeds have been increasing even as its overall size decreases. The outer ring winds, already among the fastest in the solar system, appear to have strengthened in recent years. The storm is not simply dying. It is changing form. What it is changing into is a question that depends on poorly constrained variables, how much smaller it can get before the mechanisms that sustain it fail, whether it will fragment into smaller vortices before disappearing, whether a new and different storm system could nucleate in its wake. No one knows what happens when it finally stops. The convective towers continue their activity around you. Another lightning discharge, close enough that the electromagnetic pulse is sharp and distinct. The illumination lasts perhaps 1/10 of a second. In that 1/10 of a second, you can see the water cloud layer stretching in all directions, a field of convective towers and inter-tower valleys, organized loosely into the rotational arc of the Great Red Spot's deep interior, lit from within by the chemistry of the planet itself. It is not beautiful in any simple sense. It is too strange for simple beauty. It is vast and active and lit by its own violence and organized by a rotation that has been continuous for longer than any human institution, and the feeling it produces is not comfort and not fear, but something more like the feeling of encountering a scale of time and energy for which you do not have an adequate response. You stay with it for a moment. The pressure here is between 5 and 10 times Earth's surface atmospheric pressure. The temperature is warm enough that ice at this pressure level would melt. Water exists here as liquid droplets in the cloud towers. The chemical environment is complex. Ammonia dissolved in the water droplets, sulfur compounds, simple organic molecules produced by the lightning chemistry, hydrogen and helium as the background gas. It is not hospitable, but it is active, and the activity is chemical as well as physical. The lightning discharges that fire through these cloud towers are doing chemistry. Every discharge passes a high voltage current through a mixture of hydrogen, water vapor, ammonia, and methane, the same basic ingredients that Harold Urey and Stanley Miller used in their famous 1952 experiment, in which they showed that amino acids, the building blocks of proteins, could be produced from these simple molecules under the influence of electrical discharge. The Miller-Urey experiment was designed to model conditions in the early Earth's atmosphere. The conditions in Jupiter's deep atmosphere are not identical to early Earth's. The pressures are higher. The composition is different in detail. There is no liquid ocean surface for the products to collect in. But the basic principle is the same: electrical energy driving the combination of simple molecules into more complex ones. And in Jupiter's atmosphere, this chemistry has been proceeding continuously for 4.5 billion years. What it has produced in cumulative terms is not known. The complex organic molecules that form in the upper atmosphere, the chromophores that give the great red spot its color, are partly the product of this deep chemistry, lofted upward by convection and then processed further by ultraviolet radiation in the upper cloud layers. The storm is, in a sense, a chemical reactor. It takes the basic molecular ingredients of Jupiter's atmosphere, runs them through electrical discharges and pressure cycles and temperature gradients, and produces complex molecules. Where those molecules end up is determined by the circulation. Some are carried upward into the visible cloud deck. Some are carried laterally into the surrounding atmosphere. Some descend into the deeper interior, where the pressure and temperature conditions are too extreme for them to survive. The storm rotates. The convection churns. The lightning fires. And slowly, incrementally, the storm that contains all of this, the organized anticyclonic rotation that has structured this chemistry and this physics for 300 years of human record, and an unknown duration before that, continues to contract. You begin to rise, not because the storm has released you, because the part of this journey that involves going down has ended, and what remains is the long return, not through the same layers you descended through, but through the same physics, the same pressure gradients, the same chemistry dissolving back into haze, and then into cloud, and then into the upper atmosphere. The convective towers recede below you. The lightning continues in the depths, brief and vivid and unreachable now. The ammonium hydrosulfide layer closes back above you, and then the clearing, and then the ammonia ice deck, and then the reddish-brown haze of the great red spot's interior, and the rotation, always the rotation, carrying everything in its ancient arc. The storm will still be here after you are gone. It will still be rotating, still contracting, still generating its chemistry and its lightning and its organized 300-kilometer column of angular momentum long after this moment, long after everything you know. You rise through the layers. The pressure eases. The temperature falls. The light from above returns, diffuse, reddish, scattered through the ammonia haze, and as you ascend back toward the visible cloud deck, the scale of what you pass through becomes, in retrospect, more legible. 300 years of recorded observation, more than 40,000 kilometers across at its maximum recorded extent. lightning 1,000 times more energetic than Earth's most powerful bolts. Water clouds, in an atmosphere of hydrogen and helium lit by chemistry the storm itself generates. And all of it contracting, all of it changing. The storm is still turning above you as you approach the cloud top. The reddish-brown haze, the long arcing filaments, the cold core of the anticyclone, all of it still in its slow, counterclockwise motion. You emerge back through the cloud deck. The exterior of Jupiter's atmosphere is visible again. The banded belts and zones, the other storms, the distant pale disk of the sun. The great red spot is below you, and it is, from this perspective, exactly what it has always been, an oval of rust and clay colors on the face of the largest planet in the solar system, elevated slightly above the surrounding cloud deck, rotating counterclockwise. It does not look like what you know it to be. It never did. The surface of things rarely does. The depth is invisible from here. The convective towers, the lightning, the water clouds, the 300-kilometer route, none of it is visible from outside. From outside, it is just a colored oval. From inside, it is a three-dimensional engine of chemistry and physics, running on the residual heat of a planet's formation, organized by rotation that outlasted every human empire of the last 3 centuries, and contracting slowly toward whatever it is becoming. You stay above it for a moment. The rotation is still visible. You can see the motion of individual cloud features if you watch carefully, the long filaments moving in their counterclockwise arc, the outer ring sweeping material around the perimeter of the storm. It is slower from here, more peaceful. The way everything violent and active looks peaceful from sufficient distance. The storm rotates. It has been rotating since before you were born. It will be rotating while you sleep tonight. And in the morning, when the light comes back, it will still be there, a little more circular, a little more compact, a little closer to whatever it is moving toward. But still there, still turning. You're still above Jupiter. The storm is below you, small now from this altitude, a rust-colored oval in the southern hemisphere, distinct against the banded atmosphere, unmistakable to anyone who has spent time learning to read this planet's face. But you're not ready to leave yet. There is something that the close approach, the descent through cloud layers and lightning and pressure does not give you. Scale? Not the scale of the storm itself. You have that now, 300 kilometers deep, 13,000 kilometers wide, turning at 150 meters per second at its outer edge. The other scale, the one that begins not with the storm but with the planet, and not with the planet but with the solar system, and not with the solar system but with the disk of gas and dust from which everything here originated 4.5 billion years ago. You rise further. Jupiter's disk expands in your field of view as you move away from it, not because it is getting larger, but because more of it is becoming visible at once, the curvature of the planet resolving into a full sphere as the distance increases. The banded atmosphere is clear from here. Alternating belts and zones, the dark bands and light bands running parallel to the equator, the great red spot visible as a slightly elevated oval in the south. You can see now several of Jupiter's moons. Io is closest, a pale yellowish-orange sphere trailing a faint smear of sulfur dioxide gas, where its volcanic activity is actively venting into the near vacuum of the Jovian system. Io orbits Jupiter at a distance of approximately 421,000 kilometers, completing one orbit every 42 hours and 27 minutes. It is the most volcanically active body in the solar system, not because it has an internal heat source like Earth does, but because of tidal heating. The gravitational interaction between Jupiter, Io, and the other large Galilean moons, Europa and Ganymede, locks Io into a resonance that keeps its orbit slightly elliptical. As Io moves closer to and further from Jupiter in each orbit, the tidal forces stretch and compress its interior, and the friction from this deformation generates heat. The heat has to go somewhere. It goes up through the interior, erupting from hundreds of active volcanoes distributed across Io's surface. The tidal energy dissipated in Io's interior is approximately 100 times greater per unit mass than the heat generated inside Earth. Io is being continuously kneaded by gravity, and it glows with the result. Europa is further out, at 671,000 kilometers. Its surface is ice, a global shell of water ice, fractured and refractured by the same tidal forces acting on Io, though at lower intensity. Beneath that ice shell, liquid water, a global subsurface ocean maintained in liquid state by tidal heating, estimated to be somewhere between 60 and 150 kilometers deep. The largest volume of liquid water in the solar system, possibly, other than the interior of Neptune and Uranus. And in that ocean, the question that has occupied planetary scientists and astrobiologists for decades now, possibly life. Not confirmed. Not ruled out. The chemistry of hydrothermal systems, where warm water contacts rock, producing the mineral gradients and chemical energy that life on Earth uses in similar environments, may operate on Europa's ocean floor. The Galileo spacecraft detected magnetic signatures consistent with a conducting liquid layer beneath Europa's ice during its flybys in the 1990s. The Europa Clipper spacecraft, launched in October 2024, is on its way to the Jovian system now, designed specifically to characterize the ocean and assess its habitability. But you are not here for Europa tonight. You are here for Jupiter itself, and specifically for the question of how a planet this large came to exist in this location, and what its existence has meant for the rest of the solar system. Jupiter formed first. This is the current consensus of solar system formation models, and it has significant implications for everything that came after. In the early solar system, roughly 4.5 billion years ago, the sun had just ignited, and the disk of gas and dust surrounding it was in the process of coagulating into solid bodies. The process begins with microscopic dust particles sticking together electrostatically, forming centimeter-scale aggregates, then meter-scale boulders, then kilometer-scale planetesimals, and then larger protoplanets through increasingly energetic collisions. At Jupiter's distance from the Sun, approximately 5.2 astronomical units, the temperature in the early solar nebula was low enough for water ice to condense, in addition to rock and metal. This is just beyond what planetary scientists call the snow line, the distance from the Sun at which water transitions from vapor to solid ice in the protoplanetary disk. Beyond the snow line, there is more solid material available to build a planetary core because ice is abundant in addition to rock and metal. Jupiter's core accumulated quickly. Models suggest the core reached approximately 10 to 20 times Earth's mass within the first few million years of the solar system's history, the critical threshold for what is called runaway gas accretion. Once a growing planetary core reaches this threshold, its gravity is strong enough to capture and retain hydrogen and helium gas from the surrounding nebula. The gas falls onto the core, compresses, heats up, and the planet's mass grows rapidly, not linearly but exponentially, as the increasing gravity captures more and more of the surrounding gas. Jupiter swept up most of the gas available in its region of the protoplanetary disk within a few million years. By the time the other planets were still in their early formation stages, Jupiter was already a gas giant, a world with more than 300 times Earth's mass, its interior already transitioning toward the metallic hydrogen state that defines its deep structure today. And having formed, Jupiter immediately began to affect everything around it. Its gravity shaped the asteroid belt, the region between Mars and Jupiter that we now call the asteroid belt, a zone populated by millions of rocky and metallic bodies, ranging in size from specks of dust to the dwarf planet Ceres, at approximately 945 kilometers in diameter, is not a planet that failed to form. It is material that was prevented from forming a planet by Jupiter's gravitational influence. The total mass of the asteroid belt today is roughly 4% of Earth's mass, far too little to form a planet, but also far less than the original mass in that region. Jupiter's gravity pumped the orbital eccentricities of objects in the asteroid belt to the point where collisions between them were too energetic for accretion. The objects hit each other and shattered rather than sticking together, and the resulting fragments were gradually scattered out of the region or swept into the inner solar system. The asteroid belt is the graveyard of a planet that never formed. And the Great Red Spot, spinning in the southern hemisphere of the planet responsible for this, has been turning for the entire documented history of human civilization's attempt to understand the solar system. Galileo saw Jupiter's moons in 1610 and understood for the first time that not everything orbits the Earth. That observation, 4 bright dots moving around Jupiter over successive nights, was one of the empirical foundations of the Copernican model. The planet that hosts the storm you have been inside tonight is the planet that helped end geocentrism. You hold this for a moment. Jupiter's gravity also deflects comets. Long-period comets, the kind that arrive from the outer solar system on orbits that bring them close to the Sun, frequently encounter Jupiter's gravitational field, which either ejects them from the solar system entirely, captures them into shorter period orbits, or occasionally sends them into the Sun or into a planet. The most famous demonstration of this process in modern times was the impact of comet Shoemaker-Levy 9 in July 1994. The comet had been captured by Jupiter's gravity on a previous close approach, broken into at least 21 fragments by tidal forces, and then, over 6 days in July 1994, each fragment impacted Jupiter sequentially. The impact scars, dark, irregular marks in Jupiter's atmosphere, were visible from Earth through amateur telescopes. The largest impact released energy estimated at roughly 600 times the world's total nuclear arsenal. Jupiter absorbed it. The planet is large enough that an impact of this scale leaves a mark in the atmosphere for weeks and then fades, absorbed into the circulation. Earth would not have absorbed it. The role of Jupiter as a deflector of cometary impactors, reducing the rate of large impacts on the inner solar system and thus potentially contributing to the conditions that allowed life to persist on Earth, is a subject of ongoing scientific debate. Earlier models suggested Jupiter was primarily a shield. More recent simulations, accounting for the full complexity of solar system dynamics, suggest the picture is more complicated. Jupiter deflects some impactors away from Earth, but also sends others toward the inner solar system that would otherwise have remained in the outer solar system. The net effect is not clearly protective, but the interaction is real and it is continuous. Right now, tonight, Jupiter's gravity is altering the trajectories of objects throughout the solar system. Small perturbations accumulating over millions of orbits. The solar system is not a static machine. It is a dynamical system, perpetually evolving, and Jupiter is the dominant gravitational influence after the Sun. The Great Red Spot, rotating in the southern hemisphere of this planet, is a feature of the dominant gravitational body of the solar system's planetary hierarchy. You let the scale settle. Jupiter's disk is below you, filling a significant portion of your visual field. The moons are visible, Io's yellowish-orange, Europa's icy white, Ganymede's mottled gray and brown further out. The Great Red Spot is a small oval from here. From here it looks like what it looked like to the first astronomers who recorded it, a colored marking on a banded sphere, moving slowly as the planet rotates. Not threatening. Not enormous. Just a spot. You know what it is now. You have been inside it. You have been inside the convective layer and watched the lightning illuminate water clouds that form by the same physics as clouds on Earth. You have seen the outer ring winds at 150 meters per second and the organized interior and the deep structure that the Juno microwave radiometer spent years mapping. The spot looks small from here, but small is a matter of distance, and you are very far away now. The Sun is a bright star from Jupiter's distance, not the overwhelming disk it is from Earth's surface, but clearly brighter than any other star, clearly the center of the system. At 5.2 astronomical units, the sunlight reaching Jupiter is approximately 27 times dimmer than the sunlight reaching Earth. Jupiter's cloud tops reflect roughly 52% of the sunlight they receive, a high albedo due to the bright ammonia ice clouds in the upper atmosphere, but the total solar energy input per unit area is still far less than Earth receives. The seasons on Jupiter are negligible. The planet's axial tilt is only 3 degrees compared to Earth's 23.5, so there is no significant variation in solar input across the Jovian year. Jupiter's year is approximately 11.86 Earth years. The Great Red Spot has been observed continuously for roughly 150 Jupiter years. You let that number sit. 150 Jupiter years. The Juno spacecraft, still in orbit around Jupiter as of this moment, has fundamentally changed what planetary scientists know about the planet's interior structure. Juno arrived at Jupiter on July 4th, 2016, after a 5-year journey from Earth and entered a highly elliptical polar orbit designed to minimize its exposure to Jupiter's intense radiation belts, while still allowing close passes over the cloud tops during each orbit's closest approach, called a perijove. Each perijove brings Juno within approximately 4,200 kilometers of Jupiter's cloud tops. At that distance, the spacecraft is moving at roughly 210,000 kilometers per hour relative to Jupiter, fast enough to cross the width of the Great Red Spot in less than 4 minutes. During these close passes, the instruments are collecting data at maximum rate. The Juno cam, originally designed as a public engagement camera, has produced imagery of the cloud tops at resolutions that reveal individual atmospheric features hundreds of meters across. The microwave radiometer is sampling the temperature and composition of the atmosphere at 6 different depths simultaneously. The gravity science experiment, tracking tiny changes in the spacecraft's velocity through the Doppler shift of its radio signals, is mapping the gravitational field of the planet at unprecedented precision. The magnetometer is measuring the structure of Jupiter's enormous magnetic field, which turns out to be far more complex than the simple dipole field that earlier models assumed. The picture of Jupiter's interior that has emerged from the Juno data is more complicated than the pre-Juno model. The pre-Juno model divided Jupiter's interior into relatively clean layers, a thin atmosphere on top, a molecular hydrogen layer below, a metallic hydrogen layer beneath that, and a compact, well-defined rocky and icy core at the center. The Juno gravity data tells a different story. Jupiter appears to have what scientists now call a diffuse or dilute core, not a compact, well-defined central region, but a large fuzzy zone in which heavy elements are mixed into the metallic hydrogen rather than concentrated at the center. The dilute core may extend to as much as 30 to 40% of Jupiter's radius, a region roughly half the diameter of Earth's orbit. This finding has implications for how Jupiter formed. One model, called core accretion, proposes that Jupiter started as a solid core that then captured gas. Another model, called disk instability, proposes that the gas directly collapsed into a proto-Jupiter without the solid core intermediary. The diffuse core, combined with other Juno findings, suggests that the truth may involve elements of both models, or that Jupiter's original compact core was partially dissolved and mixed into the surrounding metallic hydrogen by convective processes operating over billions of years. The interior of Jupiter is still evolving. The planet is still slowly cooling. The slow gravitational contraction that partly powers its internal heat flux is still ongoing, and the compositional structure of the interior is still being modified by the convective circulation that moves heat from the deep interior toward the surface. On timescales of billions of years, Jupiter is not static. It is a cooling, slowly contracting, internally convecting object, and the current state of its atmosphere, the belt and zone structure, the Great Red Spot, the moons embedded in its magnetosphere, is a snapshot of a system in continuous, slow evolution. The Great Red Spot, in this context, is not anomalously long-lived. 300 years is a brief interval in the history of a planet that has been operating for 4.5 billion years. The storm is young in planetary terms. Whatever preceded it, whatever atmospheric configurations existed in Jupiter's southern hemisphere before the current storm organized itself, are not recorded. The telescope was not good enough. the record not continuous enough to know what Jupiter's atmosphere looked like in the centuries before systematic observation began. There may have been other large storms. There may have been periods of different atmospheric organization. Jupiter's south equatorial belt has historically undergone those periodic fade events, and the interactions between the belt and the Great Red Spot during fade events are complex and not fully understood. The atmosphere is capable of reorganizing itself. The current configuration, the current pattern of belts and zones, the Great Red Spot in its current location and size, is not guaranteed to be permanent. It is a stable state in the sense that it has persisted for a long time. But stable states in complex dynamical systems are not forever. They can transition. The Great Red Spot's contraction is one such transition, already underway. Where it leads is one of the genuinely open questions of planetary science. Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, were the first objects in the solar system discovered to orbit something other than the Sun or the Earth. Galileo observed them beginning in January 1610, tracking their positions night after night and recognizing that they were moving around Jupiter. He called them the Medicean stars in honor of his patron Cosimo II de' Medici. They are now called the Galilean moons. Ganymede, the largest, is bigger than Mercury. Its diameter is approximately 5,268 kilometers, compared to Mercury's 4,880. It is the only moon in the solar system known to generate its own magnetic field, a localized magnetic field produced by a dynamo in its interior, possibly involving a layer of liquid iron at its core. Ganymede also has a subsurface ocean, detected by the Hubble Space Telescope through the behavior of its auroras. The auroral bands shifted in a way consistent with the presence of a conducting liquid layer beneath the ice, which partially counteracts Jupiter's magnetic field. Callisto, the outermost Galilean moon at 1,883,000 kilometers from Jupiter, is the most heavily cratered object in the solar system. Its surface is ancient, roughly 4 billion years old, a record of impacts stretching back to the early solar system, almost completely undisturbed by any geological activity since. Callisto is geologically dead. Its surface is what the solar system looked like 4 billion years ago, preserved in ice and rock, uncovered by erosion or volcanism or tectonics. Where Io is the most active body in the solar system, Callisto is among the most preserved. They orbit the same planet. They are subject to the same gravitational environment. The difference is their distance from Jupiter. Io, close in, experiences strong tidal forces. Callisto, far out, experiences much weaker ones. The distance determines the fate. You hold the 4 moons in your field of view, Io's yellowish-orange, Europa's icy white, Ganymede's mottled gray-brown, Callisto's darkened ancient surface just visible at its orbital distance. 4 worlds, 4 different histories, 4 different futures, all held in the gravitational embrace of a planet that has been shaping their trajectories since the solar system formed. The Great Red Spot rotates in the southern hemisphere of that planet. It has been rotating through all of their histories. It was there when Io's current volcanic configuration developed. It was there when Europa's ice shell thickened. It was there when Callisto's craters were fresh. It was turning then, It is turning now. You watch the planet from your position in the outer Jovian system. Io has moved noticeably along its orbit since you first arrived at this distance. Its 42-hour period means it completes roughly 1 degree of arc every 7 minutes, and the time you have been here has been long enough to see the change. The Jovian system is alive with motion at every scale. You hold your position. The great red spot completes another rotation across the planet's face. Small from here, known now from the inside out. Each of those years, Jupiter completing its slow orbit around the Sun, the great red spot rotating through its position in the southern hemisphere, the belt and zone structure shifting and interacting, the moons completing their resonant orbits, Io erupting, Europa's ocean circulating in the dark beneath its ice. 150 times. The sun rose and set, metaphorically, from Jupiter's perspective, since Jupiter has no surface from which a sunrise is visible, approximately 60,000 Jupiter days, while the storm turned. The storm turned through all of them. It is turning now. You are far enough from Jupiter that the planet's disk has shrunk to something you could cover with your hand, held at arm's length. The great red spot is no longer individually visible. The planet is just a banded sphere, slightly oblate, Jupiter's rapid rotation, completing 1 revolution every 9 hours and 55 minutes, has caused the planet to bulge at its equator and flatten at its poles, giving it an oblateness of approximately 6.5%, the highest of any planet in the solar system. From here, it is a beautiful object. The bands of the atmosphere, the 4 bright moons strung out along the ecliptic plane, the faint ring system, discovered by Voyager 1 in 1979, far less substantial than Saturn's but present, composed of fine dust particles ejected from the inner moons by micrometeorite impacts. All of it visible at once, the whole system comprehensible in a single field of view. The storm is in there, still turning, still contracting, still generating lightning in its deep convective layer, still stained with chromophores that planetary scientists are still working to identify. You watch the planet from here. Jupiter rotates quickly enough that if you watched long enough, you would see the great red spot rotate into view, complete its arc across the southern hemisphere, and rotate out of view on the other side, the full rotation taking less than 10 Earth hours. You do not have to watch for long. The spot comes around, a small rust-colored oval, rotating with the planet, exactly where it has been for 300 years of human observation. You watch it for 1 full rotation. It completes its arc and disappears behind the limb of the planet. It will come back around. It always does. You have been watching Jupiter for a long time now. The distance between you and the planet has not changed in the last few minutes. You are holding position at the same distance, the same angle, the same view of the banded atmosphere and the 4 bright moons. There is no urgency to leave. There is no schedule here. There is only Jupiter and the storm and the silence of interplanetary space, and the time to simply be present in a location that no human body has ever reached. The spacecraft that have traveled to Jupiter, Pioneer 10 and 11, which passed by in 1973 and 1974, and were the first human-made objects to travel through the asteroid belt, the Voyagers, Galileo, New Horizons, which flew past in 2007 on its way to Pluto, Juno, still in orbit now, none of them carried a human being. They carried instruments, cameras, magnetometers, plasma analyzers, spectromotors, microwave radiometers, ultraviolet detectors. They carried the capacity to measure and transmit, but not to be present in any experiential sense. The measurements came back. The numbers came back. The images came back. Galileo's close-up imagery of the Galilean moons. Juno's extraordinary high resolution passes over the cloud tops. The JunoCam images processed by amateur volunteers around the world showing the storm's swirling cloud structure in colors and resolutions that still produce a brief, involuntary pause in anyone encountering them for the first time. All of that came back, but no one was there. You are here instead, not with instruments, with the full complexity of a human nervous system capable of registering not just the data, but the meaning that data acquires when it is experienced in context. The color of the cloud material in the outer ring, the low resonant vibration of wind moving through dense atmosphere, the brief illumination of a convective tower by a gigajoule lightning discharge. All of that is real. All of that is happening right now inside the storm that is visible as a small rust-colored oval on the face of the planet below you. The reality of it does not require your presence. The storm was real before you arrived and will be real after you leave. But the experience of its reality, the translation of its measurements and processes into something felt, something present, something that has weight and scale, and the quality of encounter that required you. The universe does not explain itself. It simply is. And you are the part of it that notices. Jupiter's disk turns slowly in your field of view. The great red spot is on the far side of the planet now, having completed most of its arc and disappeared around the limb. It will come back around in a few hours. It always does. The 4 Galilean moons are arranged differently than they were when you first arrived. The orbital periods are short enough that the configuration changes noticeably over hours. Io has moved the furthest, its 42-hour orbit carrying it visibly along its path. Europa has moved a smaller amount. Ganymede and Callisto, in their longer orbits, have barely shifted. The system is in continuous motion at every scale. The moon's orbit. The planet rotates. The storm turns. The atmosphere circulates. The convective towers rise and fall. The lightning fires and fades. All of it simultaneously, right now, as you watch from this distance. You feel the scale of it differently than you did when you were inside the storm. Inside, the scale was immediate. The pressure, the cloud structures, the wind speed at the outer ring. From here, the scale is temporal. You are watching a system that has been in continuous operation for 4.5 billion years, and the storm you can see rotating in the southern hemisphere is a feature that has persisted for at least 300 of those years, and possibly longer. The boundary between the storm and the rest of Jupiter's atmosphere is not sharp from this distance. It is a colored oval in a banded sphere. But you know what lies behind that visual simplicity now? The chemistry of the chromophores, the differential rotation, the 300-kilometer route, the anticyclonic circulation that makes it a high-pressure system rather than a low-pressure one, the energy budget that scientists are still working to close, the contraction 930 kilometers per year toward a future that no model can currently predict with confidence. You know all of this, and knowing it changes what you see when you look at the colored oval. It is no longer just a marking on a planet. It is the visible surface of a deep, structured, ancient, slowly changing physical system embedded in the atmosphere of a planet that has been orbiting the sun since before the Earth existed. The silence around you is absolute. Space is not quiet in the electromagnetic sense. Jupiter's radio emissions propagate outward in all directions, threading through the interplanetary medium. But in the sense of pressure waves, sound, space is silent. There is no medium for sound to travel through. The storm you are inside, the roaring of the outer ring winds, the low resonant vibration of deep atmospheric pressure, the concussive roll of Jovian lightning, none of that propagates here. Here there is only the electromagnetic spectrum, the faint infrared glow of Jupiter's internal heat, the reflected sunlight from the cloud tops, the radio emission from the magnetosphere, visible to the instruments that can detect them, invisible to any human sense. You float in the silence. Jupiter turns below you. The great red spot is completing its arc back toward the facing hemisphere. In a few minutes, it will be visible again, the small rust-colored oval, rotating with the planet, carrying inside it the 300-kilometer column of organized rotation, the water cloud lightning, the chromophores, the vortex and vortex structure, the slow contraction. All of it there, inside the oval. All of it real. You feel the distance between where you are and where you started tonight. Not the physical distance, though that is real. Jupiter at its closest approach to Earth, sitting at approximately 628 million kilometers, and you are closer to Jupiter than that now, close enough that the planet fills a significant portion of your visual field. The other distance, the one between a human life lived at Earth's surface, under a sky where the stars are points of light and the planets are bright wandering stars, and Jupiter is just the brightest thing in the night sky after Venus and the moon, and this proximity to a storm that has been turning since before the Industrial Revolution on a planet that formed before the Earth, in a solar system that has been operating for 4.5 billion years, without pause, without awareness, without the need for any observer to make it real. It has all been here. The storm has been rotating through every human lifetime that has ever been lived, through every night that anyone has ever slept, through every morning that has ever come. It was rotating last night while you slept. It will be rotating tonight while you sleep again. The scale does not diminish you. It locates you. You are the part of this system that can look at it and understand what it is. Not all of it. The chromophore is still unidentified. The contraction mechanism is still incompletely understood. The depth of the root is still only a lower bound. But you understand the shape of it. The pressure, the chemistry, the rotation, the age. You understand enough to feel the weight of what you are looking at. The great red spot comes back into view. A small rust-colored oval, rotating with the southern hemisphere, elevated slightly above the surrounding cloud deck, counterclockwise. The same storm. 300 years of the same storm. You watch it for a while. The rotation carries it slowly across the face of the planet. There is no hurry. Jupiter turns at its own pace, 9 hours 55 minutes per rotation, regardless of what any observer wants or needs. The storm turns at its own pace, embedded in Jupiter's rotation, but also moving slightly in longitude relative to the planet's interior, drifting slowly east and west over years and decades. Everything here moves at its own pace. You begin to let go of the detail, not forgetting it, the numbers, the mechanisms, the history, the depth measurements, the chromophore hypotheses, the contraction rate, but releasing the need to hold it all in the foreground at once. It settles. The way things settle when they have been properly understood. Not into vagueness, but into a kind of quiet confidence. You know what this is. You have been inside it. Jupiter turns below you. The storm turns with it. The moons move in their orbits. The system continues, as it has continued for 4.5 billion years, without needing anything from you. You let the scale of that be what it is. The silence of the space around you. The slow rotation of the largest planet in the solar system. The rust-colored oval carrying its 300-year continuity around the southern hemisphere, still there, still turning. You stay with it until the details become the background. Until what remains is not the chromophore hypotheses or the Juno microwave data or the contraction rate, but simply this: a storm on a planet, turning for longer than any human institution has existed. Still turning now. Still turning now. The silence holds. Jupiter turns. The storm completes another arc. You feel the distance between here and sleep narrowing. Not because anything has changed. Because you have been out here long enough that the scale has done what scale always does. When you stay with it long enough, it quiets the smaller things. The pressure of the day, the noise of ordinary time. They become small against this. Against 4.5 billion years of a planet turning. Against 300 years of a storm that has never stopped. Against the absolute silence of the space between planets, where the only sound is the one you carry with you, the rhythm of your own breath, slowing now, settling now, matching itself to the pace of something much older and much larger than any single night. The darkness between Jupiter and the Sun is not empty. This is worth holding on to as the sleep comes. The space between planets, which looks like nothing from inside Earth's atmosphere, which is represented as blank white space on diagrams, as the void between labeled circles, is filled. It is filled with the solar wind, a continuous stream of charged particles, primarily protons and electrons, flowing outward from the Sun at between 400 and 800 kilometers per second. The solar wind fills the entire volume of the solar system out to the heliopause, the boundary where the Sun's influence ends and the interstellar medium begins, roughly 120 astronomical units from the Sun. The space you are in, between Earth and Jupiter, between Jupiter and the Sun, is threaded with magnetic field lines carried by the solar wind, with energetic particles accelerated by solar flares and coronal mass ejections, with the faint infrared glow of the zodiacal light, sunlight scattered by dust particles spread along the plane of the solar system. It is not empty. It is a medium, a tenuous, sparse, mostly invisible medium, but a medium nonetheless. And everything in it is in motion. The solar wind flows outward. The magnetic field lines rotate with the sun, forming the Parker spiral, a large-scale structure of magnetic field winding outward from the sun like water from a rotating sprinkler, first described mathematically by the physicist Eugene Parker in 1958, confirmed by direct measurement by the Mariner 2 spacecraft in 1962. The dust particles settle slowly toward the sun under radiation pressure and the Poynting-Robertson effect, a subtle force generated by the asymmetric absorption and re-emission of sunlight by orbiting dust particles, which causes them to slowly spiral inward over millions of years. The asteroids in the belt between Mars and Jupiter interact gravitationally with Jupiter constantly, their orbital elements being slowly shifted by resonances, locations where the orbital period is a simple fraction of Jupiter's, creating repeated gravitational nudges that accumulate over time and can eventually destabilize an orbit. The Kirkwood gaps, the gaps visible in the orbital distribution of asteroids at certain semi-major axes, are the signatures of these resonances, regions cleared of asteroids by Jupiter's systematic gravitational influence. Everything in the solar system is connected to everything else, not metaphorically. Gravitationally, electromagnetically, through the shared medium of the solar wind and the interplanetary magnetic field. Jupiter is at the center of most of these connections, its mass dominating the gravitational dynamics of everything between the inner planets and the outer solar system. The Great Red Spot, rotating in Jupiter's southern hemisphere, is a feature of the dominant gravitational body of this connected system. It is embedded in the largest concentration of mass in the solar system, after the Sun. It has been rotating through the same gravitational environment, the same resonances, the same solar wind, the same interplanetary magnetic field, for the entire duration of its existence. The solar system has not been static during that time. The Sun has gone through hundreds of solar cycles, the approximately 11-year cycles of sunspot activity and solar maximum, since the Great Red Spot's earliest recorded observation. The solar wind has varied. Comets have come and gone, some captured into short-period orbits by Jupiter's gravity, some ejected from the solar system entirely, some impacting the Sun or the planets. The inner planets have continued their orbits. The asteroid belt has continued its slow gravitational dance with Jupiter. And through all of it, the storm has continued to rotate. The 300-kilometer route turning. The outer ring at 150 meters per second turning. The organized anticyclonic circulation turning. Indifferent to the solar cycle. Indifferent to comets. Indifferent to the civilizations that developed on the third planet and eventually built instruments sensitive enough to measure its depth and characterize its chemistry. Simply rotating because the physics says it should. Because the angular momentum stored in that 300-kilometer column has nowhere else to go. Because the jet streams on its north and south boundaries contain it. Because Jupiter has no surface to provide the friction that would drain it. The physics is patient. It does not need to be dramatic. It simply holds the storm in place, enforcing the same rules that hold every rotating fluid in place, everywhere in the universe, without exception, without rest, without the need for any observer to confirm that it is doing so. You are the observer, and observing tonight, you can sleep. You let your eyes close. Jupiter is still there. The storm is still there. The moons are still moving in their orbits, Io slightly ahead of where it was, Europa following, the system continuing its operations with the same indifference to observation it has always had. The great red spot is rotating. It will still be rotating in an hour. It will still be rotating when the light comes back. In, out. The pressure eases. The temperature is comfortable now. The weight of the atmosphere is somewhere far away on a planet you have visited and will carry with you and do not need to hold on to any further tonight. You are allowed to rest. The universe does not need you to watch it. It has been here longer than watchers have existed. It will be here after. And tonight, from the silence between Jupiter and the Sun, from the distance where the great red spot is a small rust-colored oval on the face of a banded sphere, from the place where you can hold the whole Jovian system in your field of view and know what each part of it is, you sleep. If you found something in this tonight, in the storm that has been turning since before electricity existed, in the chromophores still waiting to be named, in the 300-kilometer route that no instrument has ever reached the bottom of, please consider subscribing to Quiet Science at Bedtime and leaving a like and turning on notifications so you find the next one. These stories take time to make, and knowing you are here for them means more than I can easily say. Sleep well. Everything you heard tonight is real. The great red spot is out there right now.